Okay, welcome back. So in today's PyTorch session, we're going to revisit the problem of harmonic oscillators. But this time, we will focus on comparing the three methods that we learned so far. So at the level of harmonic oscillator, implementing PARC is pretty simple. If we, go beyond harmonic oscillator with some PDE, some spatial derivative, then it can be a little, more technical. And then it's impossible that we can cover that in, just 1 hour session. So, we're going to just stick with the harmonic oscillator example. So many of this is actually something that you already know. We have, so I'm importing the libraries. We already saw this, part of the code where we define the coefficients for the angular velocity and the damping ratio. So many of this, we've seen this already. So I'm gonna be quick. But here, we're generating the ground truth, and this time we're gonna use a slightly different formulation. So instead of that original formulation that we talked about, where the input to the neural network is the position. The input to the neural network was a time, and then the output of the neural network was a position. We're gonna instead take a look into the state space representation. The state space representation, where both position and velocity is what defines the state of this system, okay, instead of a position alone. And then, obviously in this example, we're gonna be seeing a lot more, active, a lot more action going on in the dynamics compared to the previous case. So in the previous case, we had a moderate, angular frequency, and then, pretty high damping. Now we have much higher frequency, and then, the damping is, a little weaker. So we have a lot more, interesting things going on over here. The sampling of the data, we're going to use a similar strategy. So out of the entire time domain, so we have the time in between 0 to 12, and then the 1/3 of the dynamics is given as the ground truth data. And then our goal obviously is to train the model on first 4 of data, see if we can roll out the prediction for the rest in the time domain, is kind of the goal of today. Now, for PIN, there's nothing new other than maybe we have now 64 neurons for the hidden layers. So previous example, we used 32 hidden neurons. We doubled it because we have a lot more complex geometry going on. Other than that, we know exactly how to train pin. And this is almost a copy and paste from the previous example, right? So we have the data loss term here as usual. And then we have, I think the internet is the problem. Yeah, we have the physics informed loss term here, where we compute the dx and ddx, and then define the residual. So almost exactly the same. Ran this line. With this much of frequency and the, I mean, angular frequency and then the damping ratio, it's not going to do a very good job of, learning the dynamics. So let me wait for a few more seconds, for this thing to, plot the progress. But, we already know that the result is not going to be very good, right? That was kind of I get kicked out of Colab. Maybe the internet connection is not stable. Back online. Well, it is still connecting, so yeah, maybe we should do that. So because the connection is not stable, let me actually, what? Sorry about the glitch. Here is my local machine. Then let me run this. Yeah, there we go. So the training just begun, and then we have the loss and the physics loss. And then after a few steps, it's going to display the result of the progress. Right now, I set the total number of iterations to 50,000. But even if you're running longer, you will still get the same, poor result. So let me wait until 10K. Wait, let me make the screen a little bigger. So we are around 4,000. Yeah, I think I can stop over here because we already know what to expect. So I pause the training, and then here we generate the animation. So um, as we already have seen, it doesn't have a problem fitting the data loss term, but then from there it takes forever for this thing to generalize to the unseen area in the time domain. So that's where most of the training is gonna the training time is going to be spent. Now here's a neural operator. So I think we have enough of PIN, but neural operator we haven't seen it applied to harmonic oscillator example. So this is exactly the same code, as a matter of fact. So we have the spectral 1D convolution from yesterday, where we have first the real Fourier transform, and then followed by the weight multiplication, followed by the inverse of the real Fourier transform. So using that, we're building the exact same architecture. So we have 4 pieces of Fourier neural operator layer, FNO layer, and then that's basically what our model looked like. Now, in terms of the model prediction, remember the total time domain was 12 seconds, and then the training data was available for the first 4 seconds. So our plan here is to use the first 4 seconds to predict the next 4 seconds. So 4 seconds to 8 seconds. And that prediction result is going to be, again, an input to the neural operator. And then the neural operator will predict the next 4 seconds, which is going to be the 8 to 12 seconds of time interval, or something of that sort. Actually, I don't exactly remember what was the time window that I set. And since this is a Fourier neural operator, this is sort of cheating because, right, the solution function of the harmonic oscillator is already a sine function, and then the Fourier operator, decomposing everything to sine waves, right? It'll be very easy for a Fourier operator to pick it up. So there you go. Even after 500 epochs, it's a fairly good job. Especially because now the entire signal is decomposed into sine waves, and then we're doing the operation in the space of sine waves, and then obviously the solution being exactly the sine wave with exponential decay. It does a very good job actually of learning the dynamics. Although, if you look carefully, you will notice that there are some spikes. It's not perfectly smooth. The velocity is smooth, but this one is not smooth. I'm not exactly sure. But the neural operator doesn't really, relate the velocity with the position. So the neural operator doesn't necessarily know that the velocity is just the first order derivative of the position, right? We're just, predicting both together. And, as a result of that, we're getting, a result like this. Sure, we can increase the frequency, and I think neural operator will still do fine. because again, it's learning sine waves. So for Fourier formulation of the neural operator, this is pretty simple problem. So while I was talking, the solver has made a few more steps. I'm going to go down a little further. So now, for velocity, it's almost, flawless. Whereas the position, we have a little spikes. Those spikes. So first of all, I think I, made something wrong. So I said the first 4 seconds is the input, and then we're making, 4-second window. I think I made the window size much smaller. Okay. I'll have to look at the code to be more precise, but the window size is much smaller. And then using that smaller window size with the training data, we're making predictions and then evaluating the loss. But then from there, we're making predictions window by window. The spikes are actually the connection between the windows. Yeah. So the neural operator doesn't really guarantee the continuity because you're just predicting window by window. So, this window comes in as an input, you make a prediction. Now you have, a little bit of misprediction at the end of the window, but then that comes in as an input and then predict the output. So we're cutting, the predictions and stitching them together. And because of that, during the connection, there's no, smooth connection, and we're getting this spiky result. Somehow, for the velocity, it sort of managed to stitch them smoothly. Maybe the error in the velocity was much smaller than the error in the position. So again, if you train this model long enough and reduce the error, then the junctions will start to look much smoother as you reduce the error. But inherently, it doesn't guarantee the smoothness in the predicted result. So that is one important observation. But other than that, in terms of the frequency of the signal, it is almost, it is very accurate. So even though there are, discontinuities like those, the spikes like those, in terms of the frequency, it is almost perfect. The amplitude decay is the part there's, where there's a little bit of error. So I think the training is done just now, has completed. And then you can see that in the animation, almost immediately, the neural operator converges. And, to be fair, this is mostly because the solution function itself has a sine wave form. So for Fourier operator, it is a matter of just learning a single number, right? Because this complex signal in the Fourier space is just one frequency component, right? So it is a relatively easy problem for Fourier operator, but nonetheless, it does a very good job, by the virtue of learning the operators as opposed to the actual curve fitting. Now, here's, in contrast, the PARC implementation. So PARC, if you recall, is comprised of the differentiator and then the integrator, right? So the differentiator will take, will learn the derivative of the dynamics. So the time derivative of the dynamics is learned by the differentiator. And then the integrator is basically the integral of that predicted time derivative. So for the differentiator, we have an even simpler architecture where we have only 2 fully connected layers, each layer comprised of 16 hidden neurons. And then at the end, we have the layer mapping from 16 to 2. Input to the PARC differentiator is the state of the spring damper system. So the position and velocity comes in as an input. And then the derivative of that will be, returned as the output. So the time derivative of the state vector. So in that case, we have dx and ddx will be returned as the output of the PARC differentiator. And then in between the fully connected layer, we basically have the exponential ReLU. And that's how we define the differentiator model, which I named as diff. And that's really it. Okay, for this simple example, PARC differentiator is as simple as just multi-layer perceptron. Now, the training though can be slightly more complicated. So what happens is we have the outer for loop, which is for the the epochs, the training iterations. And for each iteration, what happens is we actually roll out the length of the signal. So for the entire 4 seconds of time interval, what happens is the differentiator, before that, x is initialized as x0, the initial condition. Okay. Now, for the entire time domain, what happens is we start from x0, let the differentiator make the prediction of the derivative of x, derivative of the state vector. Now, for the int, we're just using a simple forward Euler. We're not even doing anything fancy. And what that means is the predicted time derivative, okay, will be just multiplied by the delta t, okay? And that is how we do the integral. It's a very, very simple integral. Of course, you can do things like RK4 or, Hume's method or, whatever, complicated integral method. And if your dynamics is more, unstable, then obviously you will need a better integral method. But for this one, we're just using a simple forward Euler integral. So, the derivative, and that is the, the amount of change, right, of the state vector x. So what we do is to add that amount of change to the state vector itself. And we update the state vector accordingly. So here's the differentiator, here's the integrator. Okay. Now, for more complex problems, actually PARC uses a data-driven integration, meaning that instead of some sort of a heuristic integral scheme, we're actually using a neural network to evaluate this part over here. Okay. Or there can be a hybrid where RK4, for example, evaluate the integral, and then the higher order terms that are not captured by RK4 will be then learned by a neural network. Okay. So that hybrid method also turns out to be great when the dynamics is sophisticated. But here, since we are talking about a very simple dynamics, we're going to be just using a direct numerical integration method. Now, after making that update, what happens over here is we evaluate the loss term. So when time t equals to 0, we just let this part to be the loss. And for loss, we have the difference in the velocity, position prediction, and then the difference in the velocity prediction in the squared error sense. And then for the velocity, we multiply 0.1 because velocity values are, larger. So kind of balance out the position and the velocity error, we just multiply 0.1. That's an empirically determined value. And then for the later time t's, okay, we're just accumulating. So the right-hand side is exactly the same. It's just that we're accumulating the loss. So the total loss is the summation of the square difference across the entire time domain. So if you look at the procedure here, the inner for loop, what happens is we start from x0, evaluate the derivative, integrate the derivative to make a prediction of the next time step, evaluate the loss, and then we progress one more time step, make a prediction of the displacement of the state vector, and then do the integral, and then update the state, evaluate the loss, and we recursively apply that, right? And repeat the computation over the entire time domain t. And afterwards, the loss function is defined as the average of the squared error, okay, over time t. And then essentially, what we do over here is to use the atom optimizer to, make a gradient descent. And that's essentially how the training of PARC is configured. So it is slightly more sophisticated in terms of the training procedure, especially in this example we have relatively simple dynamics, so it wasn't terribly difficult. But when you have I guess more sophisticated spatial temporal dynamics data, then the training loop is going to look a little more sophisticated. And also, in case you introduce a different integration method, right, other than the simple Ford Euler, then obviously you're going to need more lines of code. So that might be the downside, compared to the neural operator approach, right? The implementation is slightly more sophisticated. But this is what happens at the early stage of training. So PARC has already figured out that the whole dynamics is sort of oscillating pattern. And from that point, the rest of the training procedure is to be essentially, tuning that vector such that, get the right frequency and we get the right amplitude. So as a matter of fact, this was at iteration 500. After 1,000 iterations, we got the amplitude, much closer to the ground truth. And then after a few more epochs, we're getting closer and closer and closer. Now, one thing to notice, though, is that in case of PARC, as we go long enough, then the frequency started to deviate a little bit. Because in case of PARC, the error in prediction at early time step will keep accumulating. So in terms of the long-term prediction, PARC has a disadvantage. To be fair, neural operators are the same. They when you go to the long-term prediction, because neural operator, for the long-term prediction, you have to do the rollout anyways, autoregressive, rollout. The error will accumulate. It's just that in the previous example, we're just basically learning. So the neural operator was still able to maintain the correct, frequency and whatnot, right? But, for more sophisticated examples, the neural operators will, eventually break if you do the longer term prediction. But PARC is more sensitive to the error accumulation. So that might be the downside of, PARC, and we're already kind of seeing that at the 2000. By the way, one thing I forgot to mention is the training data set has an artificial noise. So because the training data has a little bit of noise, we're not going to be able to find the exact trajectory, right, in the training data. And then there's a little bit of error in the frequency prediction. So instead of the actual frequency of, I don't know, I'm just this like let's say 10 hertz. Let's say the prediction, the learned frequency was like 9.9 hertz. That 0.1 hertz of difference will keep accumulate. And then as you go, longer in time step, then you'll start to deviate. Okay. So that is one, I guess, important characteristic. So I was able to, chat with somebody in the audience who's working on the, chaotic systems. So for those kind of systems, maybe, PARC is not the best choice, right? If you have a chaotic system. That's another thing. So the integral that we're using is a forward Euler, and forward Euler is known to be, very unstable and deviate pretty quickly. So again, by introducing a fancier integration method, we can go longer in time step, but eventually it will break, right? So that, I guess, is one of the downsides of PARC. And with that being said, actually one of the research direction currently is the bidirectional evaluation of prediction. So you make a prediction in one direction and then somehow go, back in time and then adjust the prediction, by looking, at the earlier time step is one of the things that we're exploring right now. But, for the scope of this course, I guess that's too much into the weeds. So it's kind of adjusting the frequency, and then as we continue the training, you will see that the frequency gets adjusted back and forth, and then it'll sort of fluctuate like that. But this is kind of what to expect in case of PARC. So I find this as a very very good example. The harmonic oscillator example, even though it's very simple, it's actually a very good benchmark problem to compare the the pros and cons of different methods. Oh, and one thing I forgot to mention is that in case of PARC, at least the predicted signal is continuous. There's no jump, there's no spike, right? As opposed to the neural operator. Because again, we're learning the transition vector of the dynamics, not the actual values themselves. So at least we have smoother prediction, but with the caveat that as you go longer in time step, it'll eventually break. But I think that's pretty much the same for traditional numerical solvers as well. So so that's a very good question. So the question is, right now we have certain delta t. In traditional solvers, if you reduce the delta t, then you tend to be more accurate, right? This is actually the part that we're kind of scratching our heads, is that in case of not only PARC, but also the machine learning based method in general, the trend is the opposite. So if you reduce the delta t, the errors start to be more significant. But if you increase the delta t, it starts to be more accurate, which is very counterintuitive, from the traditional numerical perspective. Because traditional numerical perspective, if you want to have a really precise result, you want to reduce the delta t as much as possible, then even fourth order will still be accurate. But in machine learning, it's kind of the opposite. Now, the reason that we're guessing is maybe, the differentiator that PARC learns is not the actual derivative that we're learning. It's the derivative that is somehow corrected in a data-driven manner so that this corrected, derivative times delta t will give you the right position. You see what I mean? Because the loss function is evaluated after making the prediction. So the whole point of, integral schemes like RK4, for example, is to correct the derivative, right, by referring to the adjacent derivatives. Because if you use the actual derivative and then progress in that direction, then you will quickly deviate from the trajectory because the delta t is too large, right? So methods like RK4 introduce the other references and then correct the derivative in the direction where the dynamics progresses, so that after multiplying delta t, some large delta t, you can stay on track, right? That's the idea of numerical integration methods. What's happening with PARC, we believe, is that when we evaluate the derivative, we do not take the actual derivative. We learn the derivative. We learn to produce the derivative from data. And when we do that, our hypothesis is that the neural network kind of learns to spit out the derivative that's already been corrected. And then along that derivative, if you move by delta t, you will stay in that target trajectory. Now, if you reduce the time delta t, what's going to happen is the effect of correction is not going to be as significant as before. When the delta t is big, then how well you correct the derivative is critical for the accuracy of the integral. But when you have a smaller delta t, then the true derivative and the corrected derivative, there's no significant difference. And yet, data-driven models has noise coming from data. So at that point, the noise in the prediction of the derivative is going to play more important role because we're not correcting anything at that point. So ironically, when we reduce the delta t, the errors start to grow. Whereas if you increase the delta t, because the amount of correction becomes more significant than the noise in the prediction, the errors start to reduce. So that was very counterintuitive observation at the beginning, but the more we think about it that way, the more it makes sense. So, the CFL condition, for example, that's like, simulation 101. This is like completely off of the CFL, condition, because it goes in the opposite direction. So that was actually a very interesting observation. And same thing for the neural operator in some extent. Again, neural operators are not as sensitive to the derivative, because we're not actually learning the derivative. We're just learning the. So in case of the neural operator, that effect is much lesser, but still, a lot of machine learning methods actually suffer from the same. Well, I wouldn't say suffer. It's just a different characteristic. So. Delta t, I would say, is a hyperparameter. Yeah. In general, the higher the better, but then at some point it will break. So you don't want to go with too big of a delta t. But in a reasonable range, the correlation is actually the inverse. Yeah. So if you're from a traditional simulation background, it may take a while for you to wrap your head around to to understand what's going on. But this is kind of an interesting observation, interesting difference between the neural network method versus the traditional numerical methods. So here we have animation showing the training progress. So very quickly, it converges to the overall trend, and then the rest of the training steps, it sort of go back and forth between different frequencies and fine adjustment, and then because of the error, because of the noise in the training data set, it will never converge to the precise accuracy. And then for certain extent, the prediction is pretty reliable, but then after some point, the accumulation error is going to destroy the prediction result. Any questions? All right. So I guess this is it. This is all about PARC, and if you're interested in knowing more about the full scale implementation of PARC, we have a library that's available. So here's the implementation of PARC version 1. So github.com/lab. That's our lab, Git repository. And then there's PARC. And then PARC version 2 is available under the name of PyTorch. We're not very good at naming. So PyTorch is the PARC version 2. And then installing PyTorch is as simple as just pip install PyTorch. And then over here, you will see more modularized implementation of PARC. My grad students have been, doing a great job of updating the code, and then this is kind of a live sort of document that is evolving. So as we work on new projects and work on new problems, we are updating this code base. There's also a documentation. Right now, it's not as user-friendly as I would like it to be, but at least you can kind of browse over all this functionalities, and hopefully you should be able to find a way to implement your own PARC for your own application. So for example, for the integrator, we have RK4 integrator, Poisson integrator, Hune method, integrator, Euler method. So there are different types of integrators, including the data-driven integrator. And then there's also the the differentiator design. There are modules for calculating the diffusion term, calculating advection terms, all kind of different things. So it's pretty well designed library. So if you want to, use PARC for some, full scale application, so harmonic oscillator, I mean, you can just write it from scratch, but more complicated, applications, it might be easier to use this library. Similarly, I already introduced this to some of you, but neural operator. So github.com neural operator is the sort of official implementation by the authors. And this thing, again, you can just pip install neural operator. And then inside of this library, there's a pre-implemented free neural operators, Tucker free neural operator, graph neural operators, and all kind of neural operators implemented over there. So again, you know, for simple examples, you can just write it from scratch, like what we did. But as the problem size gets bigger, it might be easier to use, you know, neural operator implemented in this official library. So there's a 2D free neural operator, 3D operator. So it's more, you know, application friendly. And then last not the least, NVIDIA has this library called Modulus. And you know, there's a official website, but there's also the GitHub library. So NVIDIA is open source again. And Modulus comes with all kind of different physics-aware deep learning models, including PIN, neural operator, and many others, many variants of those. Unfortunately, PARC is not part of NVIDIA Modulus yet, but it comes with a lot of predefined neural network architectures, different loss terms, different you know, functionalities to facilitate the use of they call it scientific machine learning, SciML, but you know, physics-aware deep learning algorithms basically are available here. So if you have your own application and then you want to have fun with the machine learning models, NVIDIA Modulus is another, you know, interesting library that you can play with. And Modulus is less user-friendly compared to the others, but once you get used to their syntax and, you know, algorithm design, you will actually find it more scalable. Okay, so again, if you have any interesting problem that you want to work on, and you know, and you want to apply physics-aware deep learning, NVIDIA Modulus is something that you can make use of, and you know, you can start from there, experiment with different architectures, different, you know, physics-informed loss terms, and so on and so forth. So you know, let me mention that. And that, unless there's other, you know, questions, that concludes technical part of the session, and then all the hands-on, you know, lab sessions. And then tomorrow and then on Friday, we're going to be looking at some of the, you know, advanced topics, as well as some, you know, applications of, you know, deep learning in, you know, solving physics problems, essentially. So we're going to look at those applications and then conceptually extend some of the concepts here to a little more advanced topics. But for those, we're not going to actually do the lab or anything like that. So today's the last time you'll be seeing the PyTorch code and, you know, things like that. So hopefully, you know, this whole, you know, series of lectures so far gave you a better idea of at least where to begin with, right? I think that's the most important thing. And then the key ideas. As long as you have those key ideas and then know where to begin with, then the rest of the details, you can read the paper. And then there are actually a lot more variants than what I explained, obviously, right? Every year we're seeing thousands, literally thousands of papers in this area. Deep learning is kind of crazy, you know, like everybody published in deep learning. It's the same thing with the physics-aware deep learning. Every year we're seeing like thousands of papers, thousands of different methods, all kinds of pin, A pin, P pin, V pin, you know, all kind of pins, all kind of neural operators, FNO, GNO, like all kind of NOs, right? So there's so many things, you know, going on. So, you know, it's hard to keep track of everything. But as long as you have the core idea, and then as long as you can connect those core ideas in terms of roughly how things are implemented, then whatever you come across in the future, you should be able to understand, you should be able to read the code and, make connection between the two. So that is really the hope. And I'm very encouraged actually by the questions that I'm getting in the class and so on and so forth. So a good job. So with that, I will conclude the lecture today, and then tomorrow we'll reconvene. We'll talk about reduced order modeling, which is an advanced topic of extending all this to more mathematically efficient learning problem. And then on Friday we're going to be talking about generative AI and all this kind of cool stuff. So thank you so much, and see you tomorrow.